So let's get into it. Today we have Nerea Lezama Ochoa and Jessie Bolin teaching this workshop for us. Nerea is a quantitative marine ecologist and an associate project scientist at UC Santa Cruz. She has a PhD in fisheries and conservation, and her main research interests are ecological modeling, spatial ecology, oceanography, and ecosystem-based management approaches, specifically for the conservation of marine top predators. And Jessie is also a quantitative marine ecologist, data scientist, and postdoc at UC Davis. She has a PhD in fisheries forecasting and climate adaptation, and her research interests include sustainable seafood, climate change, dynamic risk adaptation, ecological forecasting, and marine disease ecology. Both of their work involves modeling and forecasting using Earth system model outputs. So we're really glad to have these two experts here to share their experiences and teach us a little bit about what they know. So with that, I think I can pass it over to Jessie and Nerea. Oh,
Okay.
sorry,
Oh,
one last moment. We went through our welcome and intros. The workshop is going to be about an hour and 10 minutes, and then we'll leave a little bit of time at the end for Q&A and wrap up. Um, and there are some workshop materials which we will pop into the chat. Maybe Sam, Camilla, or Colleen, if you could throw these into the chat, that would be great. We have the GitHub repository that we'll be following along, as well as the workshop website, and then that includes some of the prereqs. And so they'll speak more to these points, I'm sure. And now I can pass it off.
thanks so much, Danielle. Yeah, hello everyone. I'm Jessie, and I'm just gonna share my screen to a PowerPoint. Um, okay. So yeah, the workshop that we're running today is essentially a condensed version of a full day workshop that we ran previously last year on working with Earth system model output in R. So we are going to gloss over some concepts today, but we do just want to say that the full notes for the workshop are open source and publicly available in the workshop notes that we've shared. So as marine ecologists who mostly use R, I guess we notice that there's a bit of a disconnect between the physical oceanography or climate science communities and the marine ecology communities when it comes to working with climate models and actually just understanding what's going on. Climate scientists, for example, they like to use Python, whereas marine ecologists generally use R, and we both have different terminology and different lingo, which makes understanding Earth system models and the whole concept of them sort of hard when you're new to the field and new to using them. So the whole aim of this workshop really is to make the world of climate models more accessible for marine ecologists using R. And so this workshop is centered around step 8 of the workflow that's presented in this paper here, which is pre-process the data. If you're going to start working with climate models, we highly recommend reading this paper. It's designed for working with climate models for all ecologists, but it has an explicit focus on case studies that are centered around marine systems because most of the authors here are all marine ecologists themselves. So highly, highly recommend this paper if you're into climate models. So today we're going to be producing projections of sea surface temperature across 2 time periods out to 2100 for 2 different climate scenarios for the California current region. And we'll get into what climate scenarios and etc. are later on. So if you are following along today and you've downloaded the prerequisites, there are 3 things that you need to be aware of. The first thing is where the scripts are located. The R and shell scripts that we're using today are contained in the scripts folder in the GitHub repo. And also make sure that you open the R project file first if you're going to be live coding as well. Second thing you need to do is go into the scripts folder and open the helpers.r file and change line 7 to the path of your working directory in your project. We've had to hard code some things and we will explain why later on, and just make sure you save that. And then third is you need to have the actual data required. We've gone ahead and pre-processed and downloaded all of the data and done all of the outputs already for the workshop, just in case you run into issues or whatever. So you'll be able to follow along regardless. You can download this folder from the link to Dropbox. It is 2 GB. But when you download that, you can just pop that into the repository because we obviously can't host that on GitHub due to size requirements. All right. So now we'll just give a brief overview of what Earth system models and climate models are in general before getting into live coding. So a climate model, also known as an Earth system model or an ESM, is essentially just a numerical representation of the world. You use mathematical laws and physical laws and equations to simulate how the climate has changed in the past and how it might evolve in the future. And so climate modelers will turn the world into this giant grid, which you can see here. And within each of these grid cells, they simulate the physical, the chemical, and the biological processes that operate across the atmosphere, the ocean, the land, and the cryosphere. And also how all of these components can store and move heat and carbon between them that warms the Earth atmosphere. So you may have heard of CMIP. It stands for the Coupled Model Intercomparison Project, and it's an international effort to improve climate models by comparing a bunch of different model simulations to observations and also to each other. And so these comparisons between models allow us to better understand how the climate has changed in the past and how it might evolve in the future. So CMIP has undergone 6 major intercomparison projects so far, and it's currently in its 6th iteration. And these climate models have been used a lot in, IPCC assessment reports since 1990. And for example, CMIP 6 was used to support the IPCC's 6th assessment report, which was published in 2021 and 2022. So the structure of a CMIP project can be quite complex and sort of hard to get your head around if you're new to it for the first time. So yeah, there's essentially 99 different climate models distributed across a bunch of different modeling centers, 49 across the world that all contribute to CMIP 6. So you've got centers in the US, in Europe, East Asia, Australia, etc., all around the globe. And each of these centers will contribute one or more climate models to the CMIP 6 suite. So this image of a wheel on the left here demonstrates how a single climate model within CMIP 6 is actually designed. So in the middle, in the white bit, you can see DEC. This stands for the entry card to be allowed entry into the CMIP suite. So this model, or a climate model, has to run a minimum of 4 different experiments within DEC that are shown in that upper right red box. And an experiment is a specific model simulation protocol that's designed to investigate a particular aspect of the climate system. And each of these experiments is designed or defined by a standardized set of boundary conditions, environmental forcing agents, and model configuration guidelines. And so this allows different climate modeling groups around the world to perform comparable simulations. So if you look at the third experiment, it's got 1% per year CO2 increase. That means that the model is running projections of a variable, like let's say air temperature, where they increase CO2 by 1% every year, for example. So that's DEC, which is one of the entry cards to be allowed entry to CMIP 6. The other entry card is a historical simulation. So now if you look at the circle, we're in the grey ring, CMIP 6 historical simulation. And this is a simulation of the past climate, where the model is run from 1850 to 2014. And every model within CMIP has to have a historical run, which uses CMIP observed forcings. So observed greenhouse gas concentrations, volcanic aerosols, solar irradiance that we've all observed like using real data in the past. And then after DEC and the historical simulation, the climate model can then run a series of model intercomparison experiments, or MIPS, that fit into into different classes. And this is like the exciting part of climate model. So we're now into the colorful part of the circle. And so all of these MIPS, these model intercomparison experiments, answer key science questions of CMIP6. So the model will run simulations that are about, changes in chemistry or aerosols, whereas other models might be concentrating on changes related to geoengineering and others about changes to ocean or land use, for example. So for today, for this workshop, we're going to use model runs that comprise experiments within scenario MIP. These are future climate scenarios that are based on greenhouse gas emissions and mitigation strategies that the world's governments take to curb emissions. And these are called shared socioeconomic pathways, or SSPs, which you might have heard of if you're familiar with climate science literature. So here is a table of the most used SSPs. You can see that they all have different levels of warming related to the pre-industrial period, and they go up in terms of severity. So if you look at the first row, SSP 119, that stabilizes global warming at 1.4 degrees Celsius by mid-century. But if you look at the most extreme scenario down the bottom, SSP 585, you'll see 4.4 degrees of warming by 2100, or projected, compared to the pre-industrial. So for today, we're going to create projections of sea surface temperature of California for two of these scenarios. You've got SSP 245, which is the business as usual climate policy, and then SSP 585, which is our most extreme emission scenario. And we chose these two scenarios because in the marine science literature, you often see these two scenarios used a lot for projecting species distribution models, for example, or other effects on marine taxa. So that's why we've chose them for today. We also just wanted to note that this piece came out last year in the conversation, and essentially says that we're headed to a 2.7 degrees warming world. And that fits in pretty nicely with the SSP 245 scenario. So even though it looks like we won't be living what's projected to be the most extreme SSP 585 scenario, but we're still going to project it anyway. And lastly, before we get into live coding, we want to introduce the two actual climate models that we're going to be using. So remember, there's over 99 of them. We are choosing one of the Australian and one of the French climate models. Both of these models are configured differently. They incorporate different submodels and they incorporate different observational data sets, etc. So I'm just going to stop sharing this PowerPoint and go to my okay, and we're going to go through how to actually download an Earth system model.
Hey, Jessica,
Yep.
could I ask a quick question?
Yeah, go for it.
Are the SSPs only available through the scenario MIP, or are the SSPs available through the various model intercomparison projects you mentioned?
Oh, I believe it's just like I've only ever gotten them through CMIP6 myself. Nerea, do you know?
I use mainly Simi 5 actually. Now we're
Oh,
starting using Simi 6.
cool.
But I don't
Awesome.
know.
Sweet. Thank you.
Thanks.
Okay. Oh, sorry.
I just said thanks.
Cool. No worries.
They are asking for that more in the papers. Most of the papers, the reviewers, are saying that we should move towards the Simi 6 actually. Yeah.
Cool. All right, no worries. Okay, so now if you go to the workshop notes, everything that PowerPoint we just talked about comprised chapter 1, what is an ESM? So now we're moving on to chapter 2, which is actually downloading Earth system model outputs from the ESGF. That stands for the Earth System Grid Federation, and that's the place that hosts all of the climate model files, essentially. So the way we download Earth system models or climate models is via shell scripts using wget. And wget was in the prerequisites. It's essentially a command that you use in Bash or in terminal or shell that allows you to download stuff from the internet, essentially. And we're going to do this through R. So if you look at section 2.2.1, we're going to navigate to the metagrid node, and I'll just copy and paste this into the chat, the link. This node I found in America works the fastest. I have found that back when I was in Australia, I had to use a different node. So if you're around the world, take that into consideration. But this is like what the homepage looks like. What we need to do is we now need to use the filters on the left to filter down to those two climate models and download what we want. So first thing we're going to do is activity ID. We want scenario MIP because we're going to be downloading scenarios. That filters a bit. Then we're going to go to source ID. This stands for the actual climate model itself. So I'll filter first to access CM2. And that stands for the Australian model. We click out, that filters it a bit more. We'll go down to variant label. So looks like that. This stands for like the realization, the initialization method, the physics processes, and the forcings data sets that are used in the model simulations. Personally, I've only ever used the R1, I1, P1, F1 variant. Yeah, I'm not sure exactly what the differences are between multiple variants, but I've only ever used that one. Frequency, today we're going to be using monthly data. So we look for the MON field, filter that. Variable ID, we're using sea surface temperature, and the CMIP classes sea surface temperature as TOS, and that stands for temperature ocean surface. So click that. Lastly, we'll click table ID OMON, that also stands for monthly. And then lastly, we want to filter experiment ID back up under identifiers. And this stands for the climate scenario. So we'll choose SSP245. And so now we're left with three options. I guess one of them has an X. That means that for whatever reason, it's not going to work when we try and download it for the node. You know, the file might be corrupted or something, so we ignore that. If it's got a question mark next to it, it means that something's wrong with the node, so we ignore that. And then we make sure we click the one with the tick. So that means the file's online, it's ready to download. So we tick that, and you can see it's filtered the file name to everything that we want. It's 255 megabytes, the file size. And if you click download options, it's got wget, right? So just to be clear, we're not downloading the actual climate model file right now. What we're downloading is a shell script that we then have to read into R to then download the actual file from the internet. That's just the way that the CMIP6 works with downloading data. So then you click the little download button and you can see that it'll download that script. So like we said before, we've already downloaded the shell scripts and everything required for the workshop in that data folder. So what I'm going to do now is stop sharing and go to R, where we can now start live coding. All right, and you can see in the data folder, oh, excuse me, I've actually put them in the scripts folder. The scripts that we're going to use to download the system models are all contained in here. That's where we've put them. Okay, so I've opened script number 2, download ESMs. First thing we want to do is read in our dependencies. This contains all of the libraries, file paths, etc. That we need for downloading the Earth system models. Next thing we're going to do is, because these files are pretty large and there's quite a few of them, we're going to use parallel processing to download them. If you're familiar with parallel, great. If you're not, it's basically a way to download or do multiple things on your computer at once. It greatly speeds up processing and greatly speeds up efficiency. First thing we do is check the number of cores on our machine. Cores is sort of like analogous to like a brain in your machine almost. You can see that my computer has got 16 different cores. So for later, I want to assign 14 to an object called W, 14 cores, and I want to leave 2 cores available for other processes on my machine, like running the operating system or watching Netflix or whatever. So my computer still runs. Now we actually define the function that we need for downloading the file itself. So the function, we've called it wgetFiles, and the function takes one argument, which is the actual shell script that we just downloaded, that wget script. First thing this function does is that it sets your working directory to where the data is going to be stored. So in this case, we're going to store the climate model outputs in the data folder called CMIP6 raw. And again, just to clarify, we have already downloaded this data prior to the workshop. The second part of this function is the actual command that we use to download the climate model itself. We do this using the system function, and this is where R runs what's contained within the system function in the terminal or in the shell. And so you can see that the argument that it uses, or the string that it uses to run in terminal, is using bash. Then it runs the actual shell script. And then we've got a tag or a flag, excuse me, for V, which stands for verbose. So you can change that to an S if you want it to be silent and you don't want to see the output. I prefer to see if there's any like errors or anything. So I just keep it as verbose. So you run that and that will actually download the netcdf or the climate model. Once it's done that, the function will then set the working directory back to the normal path. So back to, wherever you've stored the GitHub repository. So you run that, put that in your environment, and now we want to list all of the files that we want to apply this function to, right? All of those different shell scripts. So we run that, and you can see we've got 6 different shell scripts, one for each climate model and climate scenario combination, right? We've got 2 climate scenarios, SSP245, SSP585, and a historical across 2 different models. Okay, so now that we've done that, we can now run this function in parallel and actually download the data. First thing we do is we tell our computer that we want to run the function in parallel. We do that with the plan function, and you can check that it worked by just running plan by itself. And it comes up with all of this output. If you scroll to the top of the output, it'll say multi-session. And that's how you know it will work. It might be different on a Windows computer. I am running a Mac. Then once your computer is ready to run parallel, we're going to use the future walk function from the future package, I believe, so that it's going to apply that function to each of those 6 shell scripts, like in parallel. And then also, we're going to use the tick and the tock functions from the tick-tock package that actually times how long it will take. So I'm not going to run this because we've already downloaded the data and it's in that data folder. For me, with I think of my computer's 64 gig of RAM, it took about 1 minute. People in prior workshops, it's taken, half an hour to an hour, depending on Wi-Fi, computer, etc. So just keep that in mind. So once it's finished downloading, you then want to tell your computer you want to go back to single-threaded processing or normal processing, and you do that with plan sequential. And then you can check it worked by running plan again, scroll up to the top of the output, and it says sequential. So that's all well and good. Now, to check that it worked, we can list the files in the CMIP6 raw directory, right? And ideally, all of your climate models should be there that you've just downloaded. So if you run that, we've got 6 climate models that correspond to the file names for each, climate model and scenario combination that we've downloaded. And you can see that they're all NC files, which stands for NetCDF, which are very common, like file formats for the climate modeling, spatial analysis sort of communities. One thing to note is that when you're doing this yourself, I have noticed that sometimes it might download files from 2100 to 2300, for example, and you might not want that. So this is a bit of code that uses the system command to automatically delete climate models that give you data from 2100 onwards. One thing to note is that it uses the rm command. This is a Linux bash command. It stands for remove. Be very careful if you use this command, because it won't like send your data to the recycling or trash bin. It will completely erase it from your machine. So if you're using this command, make sure you 100% know that you're deleting the right file, because I don't believe you can get it back. So just a word of warning. But yeah, that's how you essentially download the NetCDF file from the internet. So before we move on to the next chapter, does anyone have any questions about that?
I have what I hope is kind of a simple question. When I ran the parallely function to see available cores, I allegedly only have 8. So am I to assume that everything will just run slower for my machine?
Yeah, it'll run slower compared to mine, but it'll still be faster than if you remained in sequential, like single-threaded processing. So yours might just take like half an hour compared to like 1 minute for me.
And so should I make W like 6 in this case?
Yeah, personally, like it is up to you. Personally, I like to leave 2 cores available for other processes to run in the background, like your operating system.
Okay, great.
Yeah.
Thanks.
Cool. All right, if there's no other questions, we'll move on to the next chapter, which is 3, remapping. Excuse me. So we've downloaded these NetCDFs, these climate models, but R has some problems with actually visualizing them. And so I'll just stop sharing my screen, and I'll show you what I mean. So what I've done here is I've opened one of these files, this one of the raw climate model outputs in a software called Panoply. The link to that is on the prerequisites. Panoply was developed by NASA, and it's a really cool data visualization tool for quickly visualizing climate data or NetCDF, like spatial data. So you can see here, this is what a file looks like when you open it straight away. To actually visualize it, we want to click on the variable name, TOS, and hit create plot. And so then I just leave all the defaults alone and I go create, and it opens up a picture of the world. And then you can, visualize your data and see how it changes through time. So that's really cool for, a quick visualization of your data, but you can't really do any data analysis in Panoply. That's where we need to go back to R. So we'll do that. All right. And so now I've opened script number 3, remapping. And I'll just clear my environment again. Okay. So now we redefine our dependencies, read in our libraries, paths, etc. And we're just going to try and plot that same file in R. And we're going to do that using the rast function from the Terra package. Just a quick note, if you are into spatial analysis, Terra is a fantastic package for doing this sort of stuff. It was developed by Rob Hyman at UC Davis, and it's the successor to the raster package, if you're familiar with that. So what we do is we just paste the file name into the rast function, run that, and we subset the first layer, and I'll explain this in a second. But we do that using double brackets, and that's like a Terra or Rust specific thing that you need to do. So we run that, and then we plot, and you can immediately tell that R cannot automatically like regrid the data like Panoply can, right? Like everything about this map is wrong. It's upside down. You know, you look at the axes, the latitudes and longitudes just don't make sense. You can see the grid, it's on this weird stretched like curvilinear grid. Everything about this is wrong. And so what we need to do is remap and regrid this so that we A, flip it the right way, 2, regrid it to a rectilinear grid, and 3, make sure that it's on a proper coordinate reference system so that the latitudes and longitudes are correct. So if we just look at the RR like object, that spat raster object, it shows us some pretty basic metadata. You know, first it's got the size, so the number of rows, the columns, and the layers in that object. It's got the resolution, and the default is in degrees. So just as a note, most climate models are served on a 1 by 1 degree resolution, or 100 by 100 kilometers. You've got the extent. In this case, the extent is incorrect, and we're going to fix that. This file does not have a coordinate reference system inbuilt into it. It's got the variable name, the units, and then the time. So we've got monthly data. So this file corresponds to January 1850. Now, if you're interested in knowing more about how the model was created and like doing a deep dive into the metadata before remapping, you can use the NCDF4 package to inspect that using the NC open function. If you run that and then run NC, in the console, it prints out a whole bunch of metadata that the climate modelers have actually like attached to the file themselves. So like who created it, what the submodels are, etc. So that's really useful if you're doing a deep dive into the climate model. But anyway, now we're going to remap this climate model using CDO and R. If you're not familiar with CDO, it stands for Climate Data Operators. And the syntax for CDO is very specific. It's deployed through terminal or the shell, and we're going to do that via R. Now, CDO comprises 4 main parts to a string of code. The first part is that you need to call CDO. So you literally write CDO. The next part is an operator. So like what you want to do to the file. The third part is an input file. So like the raw unprocessed climate data or climate model that we just downloaded. And the fourth component is the output file. So the new processed file that we do or have done the thing to. So in R, we've created a function called remap and crop temperature that uses CDO to remap and crop the climate model. The function takes a bunch of different arguments. The first is the netcdf file. So this will be the file name of that raw climate model. The second is the resolution or the target resolution, sorry, that we want to regrid to. So in this case, we're going to regrid to 0.25 degrees or a quarter of a degree. And remember, the native resolution of climate models is 1 degree, mostly. Then we've got the input folder, which is CMIP6 raw. That's where our native climate models have been downloaded to. Then we've got our output folder, and we've called that CMIP6 processed. So that's where our new and regridded data is going to live. We've then got a bunch of arguments corresponding to the latitude and longitudinal bounding box that comprises California, because not only do we want to remap or regrid this file, but we also want to crop it to just California. Okay, so now we get into the actual system function. So we use system that calls, the terminal or shell. And in the paste function, we've got a very big CDO string, right? So the first part is we tell it to call CDO. We've then got the first operator -L. That stands for lock the input and output. Personally, I just always do that when I'm using CDO. The second operator is cell lonlat box. So that stands for select lonlat box. So it's analogous to cropping. And then we've got the arguments up here that correspond to the latitudes and longitudes of that California bounding box. I will just note with using CDO, the spaces and commas are very important. If you put a space where it shouldn't be, the entire function won't work. So just keep that in mind when you're creating your own CDO like strings. All right, so that's the first part. The second part or second operator is remap bill. So that stands for remapping using bilinear interpolation. And then we've got a bunch of numbers here, and this corresponds to the target number of rows and number of columns that correspond to a 0.25 degree resolution. So that, at the moment, if you look at, let's right up here, in the native file, we've got 300 rows and 360 columns. The number of in a 1 by 1 degree resolution, that number of rows and columns will be different for a 0.25 degree resolution. So we need to make sure that we specify that in the function. The last operator is we select the variable name. So in this case, the only variable available in the file is temperature ocean surface. We did this because if you're working with your own climate models, sometimes there might be multiple variables hosted in the same file. So you might need to specify which variable you want. Then we've got the input file. So, the raw climate model. And then, of course, lastly, the output file, which will be the regridded and cropped file. So we'll run that function that reads it into our global environment. Last thing we need to do before running the function is list all of our raw climate model files, right? So we're listing all of the files within that CMIP raw folder, should be 6. And these are the files that we're going to apply this remapping function to. So again, we specify the number of cores or number of workers we want to use. We get our laptop ready for parallel processing. And now we're going to use the future walk function, which applies that remap function to each of those files in parallel, and then time it with tick and tock. And again, for me, it takes 8 seconds. Might take longer or be quicker for you, depending on your computer. And then lastly, we tell our computer to go back to single threaded processing. If for whatever reason, parallel processing doesn't work or you're having issues with it, we have also written a for loop version here that will take longer. Okay, so now we want to check that it worked and to actually visualize this output. So here I've read in one of the random regridded climate models. Here we're going to subset the first layer and plot it. Now this looks cool, but let's add the map of California to it. Awesome. So you can, if we then look at the metadata, you can see that the size, the number of rows and columns looks good. It's at a 0.25 degree resolution. the extent makes sense. You know, if you look at the axes, the latitudes and longitudes are good. Very importantly, it now has a coordinate reference system, and the correct one. And again, this is for January 1850. So that's how we can remap and crop Earth system model output. Before moving on to the next part, any questions about that? Excellent. Okay, so now I'm going to go back to our PowerPoint. The next part of the workshop is a part called bias correction. This is it's very important that you do bias correction when working with climate models for the following reasons. So, for example, the Access CM2, the Australian model, is known in the climate modeling communities to have a global warm temperature bias. So we know that it might already be producing projections that are too warm, realistically. And this is likely due to the parameterizations of clouds and aerosols in the atmospheric part of the climate model. And for this model in particular, the Southern Ocean is known to be way too hot, which then, you know, affects the rest of the world. So if we use the projections, the temperature projections from this model as it is, like what we just created, we already know that our projections are likely going to be wrong or like erroneous, and our projections are going to be biased. And this is a problem if we're wanting to do, you know, proper science like climate impact assessments or projections of species distributions, for example. You know, we want to be as accurate or reflective of reality as possible. So the whole point with this part of the workshop is to never trust the raw output of a climate model. And I guess one question that people have asked in the past about this is, how do you know what's wrong with a single climate model? And my answer is that you can read papers that have done like skill assessments of the models themselves. And these are generally published by like climate science people, generally not marine ecologists. So, you know, errors in these climate models can be due to a range of different things, like a coarse spatial resolution, you know, simplification of Earth system physics or thermodynamic processes, and just, you know, a general incomplete understanding of the global climate system. You know, these models, while they're great, they simply cannot resolve every single physical process that exists in the Earth's climate. And so this just in general can lead to bias and potentially erroneous projections. And so in an attempt to try and overcome these biases, what we do is this technique called bias correction. And there are many different ways to go about this. Some are easy, some are more difficult, and each of them have their pros and cons. In the notes, we've shown an example of probably the most simplest and easiest approach to do, and this is called the delta change method or delta change bias correction. So here are the steps. We're not going to go through them today just because of time. It takes quite a while to do bias correction. But essentially, you know, in a nutshell, what you need to do is download observed data. So in our case, observed sea surface temperature or real world sea surface temperature that has occurred in reality, you know, whether that's from satellites or buoys, moorings, or a gridded product, to create a climatology during a baseline period. And we then add that climatology to sea surface temperature anomalies that we created from projections from the climate models themselves. And the whole point of this bias correction method is to remove these mean state biases within the climate model so that the climate model projections are more reflective of reality. And so what you end up with is essentially a map on the right. And this reflects bias corrected Earth system model output using an observed sea surface temperature climatology. Now, notice we're using observations. In our case, we're using OISST. It stands for the Optimum Interpolated Sea Surface Temperature Product. It's probably one of the more famous or more generally used observed sea surface temperature products in the marine science community. And this is served at a 0.25 degree resolution, right? Quarter degree. So we now have data that's really close to the or more closer to the coast compared to the raw Earth system model, right? This one on the left, which reflects just the regridded output that we just did in step 3. So yeah, again, we're not gonna do the bias correction step, but in chapters 4 and 5 of the notes, we've given all of the code on how to download OISST, how to pre-process it, and then how to do bias correction. And yeah, I guess just another note, I tried to publish a paper earlier in my PhD where I didn't do bias correction, and like the first comment the reviewer said was like, why have you not bias corrected your output? So very, very important that you do that step. Okay, so now we'll go back to live coding. Any questions about that, by the way, before moving on?
One quick question.
Yeah.
Is bias correction like the similar method used for other outputs as well, in addition to like sea surface temperature?
Totally, yeah. You can do bias correction for any variable as long as you have an observed product. It can be current speed, salinity, whatever. Yeah.
Very cool.
Cool. Okay, so now we're going to move on to step 6 of the workshop notes, evaluate accuracy of historical ESM projections. So now we're going to open script number 6. Let me just reset everything. Okay, so now in theory, we have bias corrected, regridded, and cropped Earth system model outputs. What we need to do is check or do our own little skill assessment to make sure that our bias corrected projections of temperature correspond to like real world observations during a historical time period. So essentially, in one sentence, we're doing a skill assessment or an accuracy assessment. So what we do here, again, define our dependencies, read in libraries that we need. First thing we do is we read in a climatology, so like an average over, I believe, what did we do? 1995 to 2014. We pre-computed this, but again, the code is available in step 4 and 5. So we read this in, and I'll just show you what this looks like. So it's essentially just a raster. And if we plot it, it's the average observed temperature for that 20-year time period. Then we read in the bias corrected climatologies for both the Access CM2 and the French IPSL models. So we read those in. And again, if I just show you what that looks like in the console, instead of one layer, we've got 240 because we've got 240 months between, January 1995 and December 2014. So we read both of those in. And then we also read in the same output for the raw Earth system model output, right? So these are the non-bias corrected ones. So we read in Access, and then here, this bit of code subsets the time period because we only want 1995 onwards. The reason we chose 1995 is to match up with the same time period as the OISST climatology or the observed climatology. So we read those in. Cool. So now what we want to do is calculate the mean or average temperature of all of these fields and turn these into a data frame. So you can see here, for example, we get the Access, like, what's it called, stat raster. calculate the mean of all of those months, the mean temperature, and then turn it into a data frame. And we do that for each file that we just read in. So I'll just show you what that looks like for example, the IPSL. So again, you've got XY, latitude, longitude, and then the mean temperature, right, across that 20-year time period. Now, all this code is just merging all of these data sets together and writing column names so that we end up with one big data set containing all of this information, essentially. And lastly, we're also going to create the ensemble mean of our bias corrected outputs. And so if we visualize what this looks like, it's literally like the same thing. You've got for each latitude and longitude, like point or grid cell, you've got the average temperature across the observed climatology, the raw climate models, and the bias corrected climate models. So that's what like you need before we do a Taylor diagram. So now we've got this data frame, we can progress to constructing a Taylor diagram. And these are really cool ways of observing or comparing patterns between two data sets. They're very, very common in the climate science community when you're doing skill assessment. So I'll just run this and then I'll explain what's going on. So it produces this like half semicircle on the right. The red arrow corresponds to our observed mean, right? The OISST. And that will always plot on 1, meaning there's a 1-to-1 correlation with reality. And that makes sense because, you know, they're our observations, they are reality. When you look at a Taylor diagram, it's telling you 3 things. The first thing is the correlation coefficient, and that's on the azimuthal axis. And that goes from, you know, 0 to 1 or 0 to 100%. You've then on these blue lines, these are the root mean squared error. And then on the x-axis and y-axis, you've got the normalized standard deviation. So these 3 things together tell you how close 2 data sets are in terms of the patterns that you're trying to show. And so what we're going to do now is plot, you know, the average temperature for the raw climate models and to see how close they are at simulating reality. So first, we're going to plot the average from the access model, which is this purple triangle here. It's pretty good. I mean, if you look at the correlation, it's 0.8, nearly or just above 80% correlation with our observations. So that's cool. We'll then do the same for the raw IPSL data. Bit worse at 70%. And then now we plot the same thing for our bias corrected versions of our 2 climate models. Now, in theory, we already expect that our bias corrected climate models are going to be much better at, you know, simulating reality compared to the raw non-bias corrected versions. So let's test that. We run that. And that black triangle plots, you know, nearly 1-to-1 relationship with our observations. So that's awesome. And we'll do the same with the bias corrected IPSL model. And again, it looks like nothing happened, but it actually plotted directly on top of our observations. So this means that these bias corrected models do really well at simulating reality, at least for 1995 to 2014, or the average. And you can also see that the bias corrected ensemble mean has a much improved root mean squared error. So, you know, it's close to 0. And a normalized standard deviation of 1. So, you know, the whole point, and I'll just run the last bit of the code, which adds a legend to the plot. So, you know, this whole exercise, this whole diagram really demonstrates just the sheer value of bias correcting your climate model outputs before you go ahead and make projections. Yeah, so that's a Taylor diagram in a nutshell. Any questions about that before we move on to making our climate projections?
You said that the standard error mean for the bias corrected model is near zero. How are you seeing that?
Sorry, that was the root mean squared error. So the RMSE corresponds to the blue lines on the Taylor diagram. And so a lower root mean squared error is better. That means it's closer to observing reality. You want the standard deviation to be as close to 1 as possible because it's normalized. And that means that it's close to observing reality. So yeah, those are like the 3 rules I look for, is like standard deviation close to 1, low root mean squared error, and a high correlation.
I guess I'm just wondering, like, how do you see for that particular one, the black triangle, that the root mean square error is near zero?
Oh, okay. So yeah, so if you look at the 3 blue lines, you've got 0.5, then 1, then 1.5. So it's not actually plotting 0. But if it did like 0, it would be like
A tiny little arc.
Yeah,
Okay, so we
exactly.
can't see it because it's just that small.
Yeah, exactly.
Okay. All right, thank you.
Cool.
One
Yeah,
more
I guess.
question.
Oh, yeah.
Sorry. Is there a standard deviation that's, I guess, like, what's your threshold of acceptance, and like what would you choose, when would you choose to reject bias correction and go and maybe work on it more? When would you say it's acceptable?
I'd be interested to hear your thoughts, Nerea, on this. Personally, I would ask a physical oceanographer, to be completely honest. Because I guess one thing to note, but like we're working with sea surface temperature here, which is really well observed. We've got heaps of moorings, buoys, sensors, etc., in the ocean measuring that. And so, all of that data is then going in to making these climate projections. But if you take another variable that is not as well observed, I'm just thinking of like current speed, for example. It's not as well observed. So I, like during my PhD, I tried to make projections of current speed, and I would get really bad correlations, really bad standard deviations, like 10% correlation, with my bias corrected projections, purely because the observations that went into bias correcting just weren't as good. But yeah, honestly, to answer your question, I don't know of any thresholds. It's more like what suits you and your purpose. And I would talk to a physical oceanographer like 100% if you can. Cool. Okay, so that's a Taylor diagram. And also there are multiple ways to do skill assessments. Taylor diagrams are just one of the easiest and super well known in the climate science community. Okay, so now we can actually go on to making our climate projections themselves. We know that our projections, our bias corrected projections, are skillful. Now we can go and make some maps of temperature in the California current for our SSPs and time periods of interest. So now we go to step 7, making projections, and go into script number 7, projections viz. Okay, I guess in the interest of time, we'll skip section 7.1 time series. All of that code essentially just plots, a time series of temperature for both of those climate models out to 2100. So that's how you can go about doing that. What we're going to do is section 7.2 projections. So these are the actual maps themselves. So again, I'll just reset the environment. Okay, all right, define our dependencies. So now what we're going to do is create, as a first step, projections of sea surface temperature for both of the individual bias corrected climate models across both time periods and SSPs. So what we do here, we define both of the models that we're using, the SSPs that we're interested, and we're doing near and long-term projections. So our near-term time period we've defined is 2020 to 2040, And then our long term is going to be 2080 to 2100. So like the average temperature between those two time periods. We specified our out directory, which is going to be data projections. That's where the projections will live. And again, our input directory, so where the bias corrected maps or netCDFs live, is in there, bias correct ESM. Okay, and then lastly, a data frame of the start and end dates for our time periods of interest. Okay, so here we have created a triple nested for loop that essentially reads in the model SSP combination of interest. It then subsets all of those bias corrected months to the time period that we're interested in. So either the near term or the long term time period, dependent on the iteration of the for loop. Then it calculates the mean and standard deviation temperature of that time period, and writes that output to the out working directory as a netCDF file using the Terra package. So that's what this function is doing. I'll just run all this. It takes, what, 2 seconds on my machine, I believe. Yep, 1.5. And if we list the files that it created, you can see that it created a bunch of different netCDF files, one for each model, climate scenario, and time period combination, for both the average temperature and the standard deviation. So that's how we do that for each individual model. Now, if we go to 7.2.2, we can then ensemble both of these models together. I guess, you know, a lot of the times in a lot of papers I read on, you know, species distribution model projections or whatever, instead of just making a projection for one model, you might want to make projections for like 10 or 20 different models and then average the results of those together to, in a way or in an attempt to reduce uncertainty, right? Because each of these different climate models have different biases, different things wrong or right with them. So if you want to reduce uncertainty, this is one way of going about it. And so here it essentially does the same, this for loop does the same thing, but ensembles the results from both of these models together. So I run that and it runs instantly. And if I show you the files, here we've got ensembled projections for both models together for each climate scenario and time period combination for the average temperature and standard deviation. Okay, and now nearly at the end, we now want to look at the delta difference. The delta difference represents the change in temperature between the projected, so like the future time period, and current conditions. You know, so how much is temperature going to change or projected to change in future compared to now, essentially. So first, we define the output directory, and that's going to be, you know, data projections delta folder. First thing we want to do is create a historical average, a climatology from 1995 to 2014. And this is using the historical simulation from both of these models. So we read in rasters for the climatologies for both models, combine them together, calculate the mean because we're ensembling. And if we plot that, that's just showing you the average temperature across both models. That's all that's showing. Now, what we do is actually subtract the historical from each time period, right? Subtract the climatology from each of the projections from both time periods to show the difference in temperature. So we define both of our SSPs. It's a for loop. And essentially all it's doing is just minusing climatology from projected temperature. Run that, it should take no time at all. List the files, and now we've got the delta mean for each of those combinations. And now, finally, the fun part, we can actually visualize our projections of temperature. So we're going to visualize our long-term time period first. we're going to use the par arguments to plot 2 rows by 3 columns. That's what this is doing. And then we just read in each of our rasters and plot them. So we've got long-term SSP 585. We've got the standard deviation of that same temperature, or same field rather. And then we've got the delta difference for the long term. So 2080 to 2100. In this case, you've got a 4.5 degrees projected difference or increase in temperature compared to current conditions, or the climatology rather. So we can now plot the same for the near-term time period down the bottom. So the mean, the standard deviation, and the delta change. And the delta change from 2020 to 2040 is much less, obviously, compared to the long-term time period. And one thing I didn't say, this is for our extreme SSP 585 climate scenario. And so now, all we just do is I'll just highlight all of this code and just run the exact same thing for the SSP 245 scenario. And boom, we've got our projections of temperature of California for our time periods and climate scenarios of interest. So yeah, that brings us to the end of like the live coding part of the workshop. I guess if I want to just hand over to Nerea, just to talk about like in your, experience, where have you used, climate projections of temperature or climate projections of other variables in your work? Like how often, yeah, if you could just speak to that.
Yeah, thank you so much. It was super, super cool. Well, I'm a marine ecologist, so I definitely don't know anything about oceanography, or not too much. So usually, I always depend of other people to give me this data. And on time, at one point, depending on the collaboration, I was like, oh man, I need to also learn, to do this by myself to actually understand and the process. So, like scripts and code like the Jessie is using, I think is super helpful for us. For us, we need this information all the time. For example, one of our projects that we are doing is to create species distribution models for different protected species, and we're trying to project the distribution in the future. So I have like one slide that I just found. It's like, can share it, and I can explain this a little bit better. Yeah, let me see. Can you see it?
Yes, it's in like, yeah.
Perfect. So what we usually use is to use fisheries data, tracking data of depending the animals that we have, and then we relate this data with environmental data, that it might be in this case the one that Jessie is explaining, to create a species distribution model that relates this presence of the species with this set of environmental data. What we obtain is usually like an output that is a map of suitable habitat that is going to tell us where is the most or the preferred habitat for the species to exist in an area. Why it's important is because with these projections, we actually can project into the future this model and see if this species is going to move to a specific area, it's going to shift north, it's going to get out from specific important areas. We have several projects that we have been doing in the California current. The first one is to try to understand depending on the species. We have here, for example, the swordfish, that is a species very important for fisheries in California, and the California sea lion and the leatherback, that they are considered like bycatch, species that we need to protect. So when we project a distribution of these species, we can see also that these species, they are moving to areas out of protection, for example, or to a new areas that they are going to have more human risk. So basically, I consider that include these projections in the future models are super important. As Jessie mentioned, most of the reviewers, they were always asking about, okay, which models that you have been using, or for example, the managers, they really want to know how predictable or how realistic are these projections. So we need to include like an ensemble or be transparent and include different models. Like we have models that they project into the future like extreme events, and some of them they project less extreme events. So we try to create an ensemble of all these maps to actually introduce the uncertainty to these people and try to make it easier for them to take the decisions. We have some papers, any of you want to see actually, you know, like the progress, how to use the projections, how to apply the bias correction, how to create a model, and then actually how to see how we can use it to make a difference and in terms of conservation. So yeah, we have a lot of information, but again, just to repeat that the part that Jessie explained today, I think is probably the most important part before we run any model, any habitat model. And I think it's super interesting for ecologists to be able to have the sources to do it by themselves. Yeah.
Sweet. Thanks so much, Nerea.
Yeah.
Yeah, I guess that brings us to the end of our part. Yeah, thanks so much for coming. And yeah, any questions or anything?
Thanks so much, Jessie. That was amazing. It's an incredibly complex topic and workflow, and you did such an amazing job explaining that. So kudos. Clearly, you know this content so well. I'm curious if you could speak to like your process in developing this workflow because it's very complex and like where did you I know it's the work of a PhD and postdoc at this point, but I'm curious like how you learned how to kind of create this workflow to process these data and get to this end product, and did you rely on other people in the community and borrow code from existing projects? Did you write this all from scratch? Like I just would love to hear about how you approached it because it's very cool and yeah, obviously a ton of work went into it.
Yeah, 100%. I did not write all of this code from scratch. It was definitely received so much help from like multiple people throughout my PhD. I guess received a lot of help in understanding this workflow from one of my PhD advisors, David Schumann, who works a lot in like the climate science, marine ecology sort of community. So yeah, like I guess it was just a lot of like learning code, or sorry, receiving like code for some of these steps from Dave, and then learning parts of it myself, and then a lot of Googling, YouTube, etc. So yeah, it was definitely like a combined effort. And then yeah, Nerea and I and a few other people like created this workshop and this workflow last year, because we just realized there was such a need for marine ecologists to actually understand the theory behind climate models and how it works. I did just want to give a shout out to this new R package. Well, it's still in development, but it's called Hot R Stuff. And it's created by Tin Buenaf, who gave an R Ladies, like last year, I think. And also Dave Schumann is involved. Basically, it's like essentially turning a lot of what we like learned today into R functions that you can use like in your own workflow. So yeah, I believe it's still in development. I'm not sure when it's like going to be like properly released, but that is in the pipeline. So yeah, I'll be keeping an eye on that as well.
That's so cool. It's such a fun full circle moment,
Yeah,
because Tin was did give a really incredible talk last year as well, so that's really awesome to hear. Thank you
cool.
for sharing.
I have a question. It's maybe not so fully formed, but it seems like there's like two pieces to learn. Like there's the theory behind these models and understanding, for example, don't use the raw outputs. You have to do some corrections. There's all these steps you have to take. And then there's the actually like learning, knowing how to do that in R and how to write the code to do that. And so I wonder if you could just like speak a little bit to your experience of, what did you find the most challenging or like where did you need, I guess, yeah, I guess like in your experience, what were the bottlenecks to getting to actually like, using these data for what you wanted them to do?
Yeah, 100%. For me, probably the biggest bottleneck was the theory, like understanding like what climate models were, how they worked, what words meant, etc. Because I guess, I was lucky in my PhD in that I worked closely with a bunch of physical oceanographers, like who were familiar with this and who wanted to collaborate with marine ecologists, etc. But I guess if you don't have that, it is a bit of a learning curve, just because there's so many differences, I guess, like just, physical oceanographers use Python or MATLAB, whereas we use R, just things like that. Um, so yeah, it did take me a while to understand, different terminologies and like when a climate scientist says a model, that's different to when an ecologist says a model, because I think of a statistic species distribution model, they're talking about access CM2 or NEMO or, that sort of thing. So yeah, I really think it's so valuable collaborating with physical oceanographers, and just like getting more familiar in that space. Yeah, Nerea, did you have any thoughts on that?
I mean, it's definitely difficult. For example, I mean, I'm much older, but during my PhD, I was doing only habitat models, no climate projections. And then when I went to the Monterrey lab, that, they are basically focused on climate, every single word for me at the beginning, it was like, I don't understand. And they use acronyms too, right? So I was like, this is a total different word. Yeah, it took a while, but when you are like in, it's like really cool. You realize that you can do much more things. It's like, whoa, what I was doing, it was only in the past. Now I can do it in the future. And now I can do it with all these species. With Jessie, we have like a project that she's doing projection for abalone, in these little coastal areas. I'm doing for, like whale sharks or whatever, that is totally different scale. So I think, yeah, it opens like a lot of possibilities, and also for collaboration, like having always people next to you working is the classic thing that we have, and you don't know what he's doing. The person next to you sitting in the lab, right? So at the end, it's cool to be able to share all this and say, okay, let's do something all together.
Sounds like having the right community of people to learn from is really important.
Yeah, exactly. Yeah.
Okay, I have a compliment and a question. So I'll start with the compliment. I like totally view this work that you're doing as like the cutting edge of where bioclimate modeling like needs to go. And I'm including in that like all the documentation you've provided with this because I have been trying to track down this idea of like how to do clear bioclimate modeling really since like the first papers by William Chung were out about like shifting distributions. And I was like, I have no idea what the hell is happening. So amazing, amazing work. I really appreciate you doing this and wonder, when's another workshop gonna be to actually, tag along. I was trying to live code and I was like, I can't do this.
Oh, thank you. Yeah, we really appreciate that. I guess, yeah, like, so the last year's workshop we ran at Bodega Marine Lab, part of UC Davis. And it was more of like a pilot workshop, and yeah, like we got good feedback, it went well. So yeah, it'd be cool to run that again. We don't have any like definitive plans to run it again, but I mean, like, hey, why not? Like we've made everything open source, publicly available. So yeah, like I'm keen. Yeah.
And I'm sure this is on the website, but th there's a way to cite all of this correctly, right?
Oh yeah. Just one more thing on that. So we have published a preprint. Which I'll just link it here. Basically detailing like the summary of the workshop, what we did, why it's important, blah blah blah. And links to yeah that paper has a DIY, and that's probably the best thing to cite for the workshop. But yeah,
That's awesome.
it's all on publicly
That's awesome.
available.
Yay, good job.
No worries. Thank you.
And I do see there is one question in the chat too, which is what is usually the resolution for the CMIPs or CMIPs? Is it possible to downscale it in R?
Yeah, so I guess in my experience, the most common resolution for climate models is 1 by 1 degree, so 100 by 100 kilometers. Some are served at 250-kilometer resolution. Um, I have never tried to dynamically downscale in R because for me, that is 100% a physical oceanography. I don't know if anyone here knows Mer Bill, but like that's what she does. And I believe she does that in MATLAB. And it takes like so much resources. It can take a long time, lots of data, etc. So I don't know how to dynamically downscale in R. Maybe it's possible, but I have no idea.
Usually, for what I know, I'm gonna post here the paper from our colleague Mer that she did for the California current. They use MATLAB. Actually, they hate R to do this. The oceanographers. We always have the discussion about what is better. But yeah, this is an example. I think it takes a lot of time and data and memory. So I think with R, I think it's pretty slow. So they use as Jessie say, Python or MATLAB.
And I think they did it on the UCSC like supercomputer as well. Hey, yeah.
Yeah, exactly. We have in our labs also supercomputers that they have much more cores than our, normal computers, and they don't crash usually. Let's see, and you can just like connect virtually, just leave it running for 1 week and just do your own thing. Otherwise, it will be impossible for some of our projects.
Cool.
On that note, none of this was like downscaled in that sense. It was just remapped to a 0.25 grid.
Exactly. Yeah, we technically did like a version of statistical downscaling, the delta change bias correction, but definitely not dynamically downscaled.
I
Yeah,
see.
that is.
Okay.
Yep.
Statistically downscaled. So that's jargon one could use.
Yes. Yeah.
Okay.
So
Sick.
like,
Learning so
yeah,
many things.
there we go. Awesome. Cool. All right.
Sweet. If there's no more questions, thank you both so much for such a fabulous workshop. That was so much information. And I, again, echo others in thanking you for putting this all together in like a really beautiful resource that we can access going forward. That's awesome. So thank you so much for your time.
Yeah, thanks so much for having us, everyone. Cheers.
Yeah, thank you so much. I'm happy to come back, definitely.
Fabulous. And thank you all for coming. Stay tuned for future events from us. And enjoy the rest of your evenings.
Great. Thanks so
Thank
much.
you.
Bye, everyone.
you.
Bye bye.